Hey everybody, I'm Matthias Loibl. Thank you for the introduction. I'm, again, super happy to just be speaking for once, again. I'm a senior software engineer at Polar Signals. We do profiling stuff, which is what I'm going to talk about today. But I'm also been a long-time maintainer of various projects like Parca, what we'll talk about, Thanos, Prometheus Operator. So I've seen some things in Cloud Native. And I also been building Pura as a side project. Quick show of hands, who has heard of this SLO thing for Prometheus? Oh, so few people, wow. Okay, so quick thing about my side project, because it's like very relevant for this conference. So you just run Prometheus, and this thing will take some configuration, create recording rules, uses the PromQL parser to build the AST for the PromQL that is actually run against Prometheus, and it gives you like nice dashboards and things you can then query Prometheus for some SLOs. Apache 2 licensed, open source contributions welcome. And if you don't want to use the, I think, better UI, because I built it together with Nadine, you can also use the Grafana integration to show them there. Anyway, enough about my side project. We're here to talk about profiling. Profiling is as old as programming. So really in the 70s already, people started profiling their programs, and it was already back then helpful, and it is still super helpful today. So what is profiling? So it's like dynamically analyzing the consumption of resources. So usually we talk about the memory, CPU, or different other things, but that's usually what we're talking about. And it's kind of down to the functions, down to the line number of where the resources are being spent. There are different approaches to profiling. So one is tracing, and tracing is quite expensive, but instead because it's so expensive, you also get like everything that is happening in your system. So you like really trace everything, and you can dig into everything after the fact. Most of the time, sampled profiling is what people use. So usually that's something where you look at the program for 10 seconds, and it kind of samples, for example, 100 times per second, I think is what the Go runtime does. And after those 10 seconds, you have like 100 samples times 10 seconds. So 1,000 samples, and you can then do that a lot more with very little overhead. So the CPU and memory consumption is a lot nicer, and that's kind of why we prefer sampling profiling. So why would you profile, right? You want to improve performance. So imagine you're some e-commerce shop, and you want to like really make sure that like the front page, or like generally speaking, everything loads within 100 milliseconds. Kind of a golden rule in e-commerce to be beyond that, below that threshold, just to make sure that you are actually having a nice experience for your users, and they can spend all the money. But also you want to save money on your infrastructure, and it turns out that 30% of organizations can save up to 30% of their resources if they just like looked at some more into the programs and what they're doing using, for example, profiling, and you can save, like 30% of CPU is quite something oftentimes, right? So just as an example, because Go is so nice when it comes to profiling, we'll talk about Go, but we are going to also dive into different programming language later. And Go comes with a super nice tool called pprof, and it comes from the Google Performance Tool Suite. And it's already built into the Go runtime. You can do a few things, and you get pprof into your programs, into your applications, and you can start profiling them. The nice thing about pprof, it's an open standard, and it's like interoperable. It's a well-known format. It's, I think, defined in protobuf. So not even only Go can use pprof, but anything can create pprof profiles using that pprof format. For other languages, exactly. You can see just how nice Go has added pprof into the runtime. There are some community projects for Rust, Python, Node.js, and also the JVM. But again, we'll talk about something eBPF based that's allowing you to do more things easily as well. So if you have these pprof things enabled in your profiling in your programs, you can then use the go tool pprof command, for example, if you're using Go, and this will actually go to localhost 6060, pull down a profile. Like it will take 10 seconds because it's like observing it for 10 seconds, and after 10 seconds it will open a HTTP server on port 8080, and then you get a UI with like flame graphs and also like a call graph where you can then introspect what has been happening and where the CPU, or like in this case, I think the memory has been spent in your program. The way it works, you have the stack trace, or like your actual code, and you can see there's the main function, and we have two functions called from the main function. It's the iterate long and the iterate short. One does, I think, 10 billion iterations. The other one only a tenth of it. So yeah, we can see later on the difference, but we are going to look at like the main function calling iterate long, and then the iterate long calling the iterate function, and we are kind of like folding that into something where you can see like the stack trace in a clear way as kind of a linked list in a way. And then once we have those laid out in such a format, we can then basically use a symbol table internal to pprof and then reference location IDs to those strings, so we don't need to repeat ourselves. And that's what the location ID is for. And we again have like all the different locations and then the actual value that we observed within, for that specific stack. Yeah, this is how you do it in Go if you want to expose pprof. For then the Go tool pprof thing to be able to pull it down, you need to add these couple of handlers and start the HTTP server. And now you can see like the third one is like the profile endpoint where you can then get those CPU profiles from. Also with Go, they just shipped in 121 the profile guided optimizations. I think Rust has something similar and a bunch of other languages. But yeah, Go finally ships this so that you can take a profile of your program and then feed that CPU profile into your compiler of Go, and it will actually use that information to speed up some things. I think it's doing inlining for now, and there are like different ideas on how to improve that even further. So that's super exciting to me, obviously. Profiling is incredible, so as we just heard, but the problem is it's just a snapshot, really, right? So we have to run this command. It's like manual, and if it's running somewhere else, we might not want to expose this endpoint to the public internet. And yeah, we have a bunch of toil at hand, so that's kind of the problem. Even though it's great, it's still manual, and we want to solve this somehow. And that's where continuous profiling comes into the picture. And we were actually inspired by this paper while we were building Prometheus and Thanos and all of these things in Go. We often, obviously, had to use pprof to figure out what the hell was going on. It wasn't always obvious, but profiling always helped. But it was always so tedious, and then port forwarding and all of these things was just a bit tedious. So we wanted something that could run next to our actual Prometheus instances, for example, and just scrape those every so often, for example, for pprof. So yeah, that's the why. And it's also because you want to actually do this in production. The funny thing is, with the sampled profiling, you can do it in production. There's not that big of an overhead. So we basically always have it enabled, and we see actually the hot paths in production because development usually hasn't the same amount of load on the system. And for continuous profiling, we get all of the data and context over time, right? We want to be able to see when did a rollout happen, what was the difference between those, etc. So again, we can save money, we can understand the difference, and we can also understand the incidents. Again, if a rollout just happened, we then know where it started, and we can instantly see memory spike or like CPU like using way too much time. Then we know, okay, something happened, and then we can even, in best case, compare the old deployment with the new one and figure out exactly where the problem actually is. And that's a really, really common thing. I don't know, please shout what it is. Can you guess? It's the memory usage. Anyone? Umkill? So this is what we're seeing in Prometheus instances, for example, or like in different other applications, and then it starts over, and then, yeah, it gets killed again, which is not nice. And like with just metrics, you can alert or you can see it, but you don't really know where deep down in the stack the problem actually is, right? So, or actually to make the more interesting point, that's why we have the slide. The problem is that the umkill happens, and we just we can't really tell when the umkill will actually exactly happen. So we kind of like manually need to like, probably now, and then like get the profile, and then, okay, we were too late, and we don't have the profile, right? Kind of sucks. So we want to have this like always on, and we want to be able to like kind of time travel back, and then get the umkill that was like so close to where the profile so close to where the umkill actually happened. Yeah, and how can we achieve this? So we are going to store those profiles over time. We can index the data with some labels, and kind of like we'll look at that. Similar to what Prometheus has, we use the same label, multi-label labeling, and then we can also use kind of a simple query language to find out which exact profiles we want to look at, and kind of slice and dice the data as we need it. The way it looks from when scraping, for example, pprof endpoints, is that we get one profile, and then similar to what Prometheus does, we scrape another one, and so we have like this paper trail over time of all the profiles, and then we can like either like say, I want to look at this specific one, or I want to crunch a bunch of numbers and look at like all the profiles over time for CPU, for example, and then we have like the nice thing that we can look at all four in kind of a single pane of glass. And yeah, the gist is we can always profile in production all the time. Again, we just run it constantly, and I think most of our customers actually run it always on as well. They kind of start out testing it in staging environments, and then they build confidence, and all of a sudden realize, yeah, it's like super useful, and the overhead is definitely worth it. And kind of interesting aspect of it is like once you have the data, you can actually save a bunch of resources, so it kind of like becomes a negative overhead, right? And yeah, we started out wanting something like a continuous profiling thing, like a Prometheus, just for profiling, right? And that's why we created Parca. Actually started out as conprof, if some people have seen the project around, very imaginative name, conprof, but we rebranded it as Parca and have done tremendous work since. I mentioned Prometheus a couple of times. I don't know who looked at the architecture diagram of Prometheus. It's super similar to Parca as well, and we have like a Parca server in the middle. It can like go out and use service discovery. We actually use the Prometheus service discovery as well, so we can discover all the same targets, use the same labels, etc. So you can copy paste label matches from one to the other, and then we can scrape those discovered HTTP endpoints. We can then store those profiles in object storage and for a bit longer term storage, and obviously we have a web UI to then display and query the data that you want. And there's like this little thing called the Parca agent we'll talk about in a bit that actually doesn't scrape, it actually pushes. So Parca, yeah, Parca is open source, Apache 2 license. We have a neutral governance, although we would like more contributors. We only have one outside contributor right now, so that there's your chance to get your changes in. But yeah, we're definitely open and welcoming contributions. It's, again, inspired by Prometheus. We also just have a single statically linked binary. So we want that experience from Prometheus of like getting the binary, running it, and then it starts doing stuff, right? Yeah, the multi-dimensional Loibl model is something we really enjoy using for all the things that you might know about and why it's great. Yeah, and the other ones I already mentioned. So this was the little box on the side, right? The Parca agent. And who has been to the keynote 2 days ago? All right, that's a lot. So you all know about eBPF at this point, right? No need to explain anything. But yeah, like briefly looking into it. So we have the process, and the process can use a syscall to then load this like small snippet of an eBPF program into the kernel to kind of extend or yeah, say something more specific what we want to do. And we can use the verifier and in some cases also JIT compile those eBPF programs. And then the process again can use, for example, syscalls to, in networking cases, observe sockets and TCP connections, and then gather some data like that from the kernel. We're actually not using syscalls, so this is just a eBPF picture on how it works. We don't use syscalls to retrieve the data. We'll talk about that in a second as well. Yeah, and that's the second. The Parca agent then loads the eBPF program from user space, and the eBPF program starts writing the observed profiles into these eBPF maps. And the Parca agent only every 10 seconds goes into eBPF maps, which is like a data structure within the kernel, and then can read those profiles or like that data. At that point, it's just some data structures from the kernel and then do something with it. But the point being, the kernel, in our case, observes stack traces 19 times per second only, which is like, if you're looking over like minutes and hours worth of data, it's 19 times per second is just fine. You can catch all the hot paths and the things you probably want to improve. And then the agent only every 10 seconds looks at those 190 in between samples or like observations from the kernel. So that's why it's relatively low overhead, especially with the agent. And yeah, there are K-probes, U-probes, different custom hooks you can use in the kernel, and we basically right now only use the perf event, which is kind of a observability toolkit for eBPF, and it's been going really great so far. So once we have those eBPF maps, we kind of retrieve them, and then we have, in best cases, if there are frame pointers, like the kernel always has frame pointers enabled, it will already tell us all the memory addresses it has been seeing. In some cases, we don't have that luxury, so we actually need to use stack unwinding to then, from all of this, get to a place where we can have stacks with proper physical or virtual memory addresses. And I mean, I don't know who can read this, not really helpful, right? So we use binaries, dwarf usually. Go has like the Go program counter line tables, I think that's what it is. And we can also use those. We might use them more in the future, but we're actually trying to use a dwarf as much as possible to then take the symbols out of the dwarf headers and enhance the memory addresses with the symbols. So it's actually becoming human readable. And that's kind of what we mean by that, right? We have the memory addresses. In this case, we're actually using the Go tables, but in a similar way, when using dwarf, we are also doing a bunch of similar things. So we end up with those actual symbolized stack traces. For the kernel, for example, we always symbolize in the kernel or like close to the Parca agent, because it's like dynamic and there are some things that might change depending on the system. Same for like interpreted languages. We always have to symbolize those in the Parca agent. But for compiled languages, we actually have debug info, and we can use those to then only ship the stack traces with the memory addresses using a build ID, and the build ID is unique for that specific object. So if you compile against some linked objects, we can only upload those once. If you have like libc, for example, we only ever upload that debug info once, and then we only ship the memory addresses from there, which is saving a ton of bandwidth, obviously. But in some cases, again, kernel-interpreted languages, we always have to symbolize. Yeah, that's kind of the nice thing. It's a single profiler using eBPF, and it can like discover, not really discover, it just like starts globally profiling every process in your infrastructure. And by doing that, we then only have like PID has like those profiles, right? But we can then use different techniques to enhance those profiles in terms of labels, so we can add more metadata to those profiles, and for example, add like Kubernetes labels or systemd unit file names, things like that. So it becomes more descriptive again what that specific PID is actually, what that actually is. Given we are at SREcon, we need privileges to run eBPF, but we are very aware of it. So we try to have as few dependencies as possible. We use statically linked compiled binaries. We use the core E, compile once, run everywhere, which is kind of a nice new thing in eBPF as well. We have reproducible binaries, so you can build them on your machine, and you will get the same byte by byte output. And we are also signing the containers. Just to not miss any of the updates, security fixes, etc. We have like Dependabot or RenovateBot to just make sure that like if something happens, it automatically ships into the next release anyway. And then for like if you have programs that are kind of internal and private, we never actually ship the binary section, the executable section of your binary. We only ever ship the dwarf symbols, right? So even though we can see which functions you have in the program, which names they have, etc. We never know more about it other than those function names and then how often they show up. Low performance, and then the additional metadata. The additional metadata, which is helpful for correlation. Again, you can, given that we use like Prometheus to discover things, we can copy paste labels from one system to the other and find the same things. There are like other projects by our friends at Grafana who are doing similar things, so kind of integrating with the entire ecosystem there. And just recently, we also added support or like general support for pprof labels. So in your Go programs or different other programs, you can then, for example, into profiles also add trace IDs, and those will be then also sent along with the profile, so that you can even like from a profile go to a trace in a tracing system. We are super excited to just recently finally have been unlocking the ability to profile Python and Ruby, and that specifically with a zero instrumentation, right? So the agent starts, you don't need to do any code changes, not for your compiled languages, and also not anymore to Python and Ruby. So that's something that's super, super exciting to us. And the reason why we needed to do some extra work is you have like the stacks from the interpreters, and you can see the interpreter actually doing things and like using CPU, but you couldn't actually see the stacks and the profiles that you wanted to look at, like from your actual program that the interpreter was interpreting. So we needed to basically do some work to get to make it possible to have the abstract stacks that the interpreters have internally to be able to walk them, find the memory addresses, do some of the symbolizations, etc. again. And with that, we now can have like super nice flame graphs. And again, like the top, the greenish thing was like the interpreter in the flame graphs. That was always there, but the highlighted blue, darker blue ones, those are the actual interesting stacks or functions that you want to look at, and that's something we are able to do in Python. Most of the like recent versions, etc. Read the docs on which versions exactly. I don't know. And for Ruby as well. And you need to make sure that every Ruby version has like slightly different things. So we have to have like integration tests and figure out the exact memory addresses where to start walking the abstract stacks. But again, now you can see we have the main function, and that's calling some other things that are actually written by the user. So we've seen the slide earlier on with like pprof endpoints, etc. And we had some things in here, but now like some languages, but now we actually have a bunch more language support. And the cool thing is using eBPF, most of the languages don't need to do anything. For Java right now, you need to add like a flag when starting, for example, the JVM, but hopefully we'll get rid of that as well. And then the cool thing is that we can use eBPF to create pprof, so using the open standard pprof profiles in the Parca agent, and then ship those off. So it doesn't even matter which language to some extent it is anymore. We can just gather pprof profiles. Yeah, and those work without frame pointers. But if you ever build something, please don't throw away frame pointers. It's not really worth it. And we actually, I think, convinced Fedora, for example, to not do this anymore, and yeah, made everybody's life easier. So the Parca agent, to summarize, it's open source, and it discovers everything. It enriches the metadata from Kubernetes systemd, Docker, etc., uses eBPF, and then yeah, only 19 times a second observes your stacks, and then only every 10 seconds reads those eBPF maps. And the best thing is no code changes are required. So how can we visualize all of this? Again, I already mentioned flame graphs. So basically what we, yes. So basically what we do is we have these stacks and we observe them and we kind of collect them, right? That's what we're doing in the kernel, for example, and we just write them to a map, and we a bit aggregate them on how often we've seen a stack. And then we have this like random collection of stacks that we were observing, which is helpful, but we can do better. Google Slides and videos. So we then use, for example, alphabetic sorting of the function names to like actually sort all of these stacks into like every level, starting kind of alphabetically. So that gives us the nice advantage that like all the functions with similar names are close to each other. And then if they actually have, for example, the same function name, go for it. Then we can combine all of those into like a wider span and have them actually be shown across the flame graph, and you can more easily read things. Otherwise, they would, like the function names, you could always only see the first letter. So this is what it looks like. You can see different colors for different things. So the Go runtime actually is highlighted here. The kernel is highlighted here, although it's kind of the same color in this picture. But yeah, you can see the different parts of the stack and where it comes from. If you want to dive deeper into really understanding how Icicle and flame graphs work, by the way, Icicle is just when the root is on top and they go down. Flame graphs is if the root is at the bottom and they go up. That's all there is to it. But yeah, if you want to really dive deep, Kemal has written a fantastic blog post. Again, I also only know so much, so I learned a ton from that blog post. If you just want to look at the table, that's also there, and then you can like figure out some more with a table if that's what you like a bit better. And then something we've recently added, and I think this is super, super cool, is the source view. So basically, you click on a function, and if we have the source code available, you can then open that from the flame graph. There's like this little open in the tooltip, and it opens the source code that gets uploaded alongside the debug infos. And then if that's something you want to ship, we can show like inline what a specific line has used in terms of cumulative or flat values. So quick demo. Let's see if this works. Just to show you it being interactive. Conference Wi-Fi. Change the background color. Okay, given time, maybe we don't do anything live. Yeah, I think it's the Wi-Fi. Well, we tried. I would love to show you, but yeah. we can do a demo. You can find me at the conference for the rest of the day, so feel free to approach me. Also, I guess a bit more interesting again, if you're saying like, okay, like flame graphs and like profiling is super interesting, but like how can I actually use this for my programs, right? We've been kind of like enjoying live streaming on Twitch and in this case YouTube. So we're like, for example, like the kubelet or the Prometheus node exporter, Kubernetes metric server. We've been like looking at the profiles, looking at the flame graphs, and then diving into how we kind of approach finding things, how we can improve things, and sometimes not even code changes are required. Like one time we streamed, it was quite funny. We just saw in the profiles, wait, we have like the node exporter Btrfs collector on, but we're running on VMs that don't even have that file system. So why are we like spending 10 or 5 to 10% of our CPU on running that collector? So all of a sudden it was as easy as like disabling this in the node exporter. But yeah, it's fun. We interact with everybody in chat, and it's a great learning resource there. So for the storage, we needed something, or we started out actually forking Prometheus TSDB, but every single function eventually became its own time series, and we all know and love Prometheus, but it has the cardinality limits, right? So we knew right now when we started, it was great, it was working, but we needed something better. So we actually written a database from scratch. Great idea. It's called FrostDB, and it's written in Go. It's an embeddable columnar database. And one of the things why we actually have written this database is because the labels we have for storing kind of the Prometheus-ish labels, we actually made those first-class citizens in the database. So we have like dynamic white columns, if that's something that you're interested in. But yeah, we kind of use a columnar store instead. Even though it looks a bit like a time series, it's not really a time series when you look at it closer. And yeah, Apache Arrow and Parca is what we're using, and they're pretty great. So now that we have like the data profiled and we need to store it, we get all of these like labels for pods and nodes, and those are the ones that are dynamic, for example, when you have the labels prefix. And then the stack trace, which are usually just memory addresses stored, but for this example, we wrote the names. And then, yeah, using columnar data, we can actually compress a lot of this after storing it on disk using Apache Parquet, for example. We can really compress a lot of these things. On the right-hand side, you can see the timestamp and the values. And something that Arrow is actually quite nice in, it has already for Go as well, it has a single instruction, multiple data. So you can aggregate a lot of int64s using the actual CPU instructions, which makes it just super nice and fast. Again, how do you query all of this? We have a Prometheus-esque query language, so the curly braces, you have the label matchers, and then at the front we have, I mean, it's simplified, but basically you want CPU samples or CPU nanoseconds or whatever profile type you want, and you give it the time, and you get that specific profile. Or what we usually do is we give it a start and an end timestamp, and then we aggregate and merge all of the profiles within that time range. And the way it works is we look at the samples from the profiles, and then we look at each sample, and if it like shows up in multiple profiles, we can just like do the aggregation, right? And then that's why we have like the possibility to have profiles over an hour into one single flame graph. And then the other one is the comparison. So before a rollout, after the rollout, something changed. We can see, we can compare these like stack traces, and for the first one we see we gotten better by 4, and for the second one on the right-hand side we see we gotten worse by 2. So you can actually start comparing them. And if the demo would have worked, I would have been able to show you. So something we're super excited about, we finally, after 2.5 years, have our Polar Signals Cloud GA. So if you don't want to run Parca yourself, we have kind of a Thanos-ish thing internally that scales horizontally. But yeah, just something to be aware of. However, we still have Parca as an open source project, and we want to grow it. We want to have more maintainers. We have the neutral governance, and you can be part of adding more and more and more to Parca, and make it just be perfect for your use case as well, right? So please feel free to join the Parca Discord. We have Parca office hours every 2 weeks, different time zones for APAC, for North America, etc. So we kind of like alternating there. So hopefully everybody can find time to join. If you have questions, if you want to just ask questions, or if you want to discuss PRs or issues, we're always happy to do that. And here are some resources, and that's it.